I'm Deepak Kapa, a junior majoring in engineering physics at IIT Roorkee. Today I'm going to be explaining the basics of control theory and the simulation of an inverted pendulum on MATLAB Simulink for my course in Systems and Signals taught by Professor Mayank Goswami at IIT Roorkee. So, what is control theory? Control theory basically tells us how we can get a system to do something we want it to do. It gives us like the mathematical tools required to develop an autonomous system. So this autonomous system can be an automatically driving car, a packet sorting arm, or the temperature control in a classroom via an AC. So how do we model a system in terms of control theory? So say I have a system, in this case it's a car. So the car is going to have two sets of inputs, one the controlled inputs, which the driver has control over, that's the steering wheel, a brake, and the accelerator, and disturbances like bumps, people, and gusts of wind, and the states of the system. So the states of the system are how we measure where or how the system is. So for a car, that would be the speed, the direction, and the position. So say a driver wants to go from point A to B, he's gonna he's gonna start by pressing the accelerator and then braking whenever he sees a bump, or whenever there's too much wind to one side, he's gonna turn the steering wheel to counter the wind. So basically, a person decides how to do all of this. So usually, what control theory does is it's trying to eliminate the person and do it autonomously. So what are the ways we can do this? So one of the ways is called open loop control, and those controllers are often called feed forward controllers. Basically, what a feed forward controller does is, based on solely one input only, the feed forward controller has essentially one input that's called the reference variable. What the reference variable is a measure of, it's a variable that tells the system what we want it to do. So say I want to go from point A to B, so this goal would determine the reference variable, and based on this reference variable, the feed forward controller would generate inputs, like a set of inputs that would be feed it into the system at one go. So say I want to go from point A to B. So what my feed forward controller is going to do is going to tell my car to go 50 meters straight, then take a right, then go 50 meters again, take a left, take a right, and take a left again. So at one go, I just told my system to do everything. So basically, this feed forward controller does not need any, it does not have any reference between the states of the system. So it does not know what the system's actually doing at a certain point of time, but just gives the system all the inputs it requires to reach the final destination. Often feed forward controllers are very complex computing wise, and they don't counter for any unexpected disturbances that can come. Like suddenly, suppose the car expected, like there was a huge cyclone or something, and the car just turned. There's no way the controller knows this, so it's just going to go to the wrong destination. So to fix this, there's another set of controllers which are closed loop, and they are called feedback controllers. So how these feedback controllers work is, feedback controllers have two sets of inputs. One is the reference variable, which is the measure of the desired work that we want the system to do, and two, the current state of the system. So based on this, it subtracts the uh, current state of the system from the reference and generates something called an error. So based on this error, it models the system. So this error is like the function or the essential goal of the, is the essential input of this feedback controller, and based on that the system works, and then the system encounters disturbances, and then again this happens. So basically, now if there's a new disturbance, that's going to change the state of my system, and this change state is going to be feeded back into my feedback controller, and now the feedback controller has an opportunity to respond to this unexpected disturbance that happened, that is not there in a feed forward controller. So that's why feedback controllers are often better. However, feedback controllers have an issue. Even though they're very powerful, they're often said to be dangerous because they change the dynamics of a system. When a controller changes the dynamics of a system, it can do two things. It can make the system more stable, or it can make the system more unstable. So a control engineer has to be very careful when he's designing such a controller, because it can make a system unsolvable, and it can make a system worse. So we don't want that. So that's why we have to be very careful while designing feedback controllers. So there are many types of feedback controllers. I'm going to roughly talk about a few of them. The most basic and often sometimes the most used one is the PID controller, which it's a type of linear controller. I'll talk in more detail about it later on. And a non-linear type of controller is a sliding mode controller. One set of controllers are called the optimal controllers. What these optimal controllers do, one example which I've written here is LQR, that's linear quadratic regulator. So what these optimal controllers do is they make a cost function between performance and effort that the controller does. So say I want an X amount of performance, I need to put Y amount of effort to this. And then based on this, you decide whether that controller is worth it or not. If the amount of effort you're putting is being translated into enough performance or not. And another type of controllers is the model predictive controllers. They're often called in the short form MPCs. What this does is this controller itself has somewhat of a model of the system within the controller itself. So when you feed in the state of the system, it can predict what the future state would be, and based on that, it changes the input, and that is fed into the system. And a newer set of controllers are called intelligent controllers. An example of them are fuzzy logic controllers or reinforcement learning. So basically, what these controllers do is you don't have to model anything. Basically, you teach a controller whether it's doing the right thing or not. So you have a controller, and if it's giving the desired output that you want, you say yes, that's a good output. If it's not giving, you say no. So basically, usually what happens is the good inputs or the desired outputs have a positive value, and the undesired ones have a negative value. Based on this, you're somewhat teaching the controller whether it's doing the right thing or not. But then the issue with these type of newer intelligent controllers is even if there's a slight error, the algorithm that is created is so complex that you can't make changes to it. Like a human can't make changes to it. So we can't really use them that well because even though there's a slight error, I have to redo my complete learning process. So usually what people started doing these days is they started clubbing these model based controllers and intelligent controllers to generate a new set of controllers, which often right now I believe are the best working controllers. Hi, so let's talk about the PID controller right now. PID stands for Proportional Integral Derivative Controller. It's a linear feedback controller. So basically, what this does is it has a state of the system X. It's going to subtract it with the reference variable to get the error, like all the feedback controllers do. And now this error is going to be the input of the controller. So what this controller does is it has three different gain cycles for the error. So one is the KP part, is the proportional part, and Ki, which is the integral of the error time graph, and the Kd part, which takes the slope of the error time graph. So if you look at this diagram, if I want to get the controller input at this particular section, so what the Ki part is going to do is going to multiply it with the area up to this section. The Kp part is just going to multiply with the value of error at that point, and the Kd part is going to multiply it with the slope of the error at that point. So I can show you the MATLAB PID model. So this is MATLAB Simulink. This is the PID controller. So this is the compensator formula of the PID controller. If we can look where my mouse is hovering, there's P, there's I and D, which stands for KP, KI, and KD. So basically, P part is directly multiplied with error. The I part is multiplied with the integral of error. 1 by S is the integral. And the D part is multiplied by N into 1 plus N into 1 by ds. See, 1 by S. So basically what this is if you use an approximation, since N is 100, which is much, much greater than 1, you practically get ds itself, which is the derivative part. So now going back to my notes. Yeah. So now I'm gonna explain each part of the controller and why it makes sense altogether. Okay. So coming to the proportional part, say I have a robotic arm and I want this robotic arm to move 90 degrees. So I'm gonna make a reference angle, which is gonna be my 90 degrees because I'm assuming the initial state to be 0 degrees. So what is my controller going to do in the first cycle? Okay, so and also one more thing, I'm using only the proportional part. So my KP value, which is the KP proportional gain, is 0.6 in this case, okay? And my control input is the angular velocity of the robotic arm, of the elbow joint of the robotic arm. So what happens now is, since I told you my state of the system is initially 0, the reference variable is 90, the error is about 90 degrees. So this is going to be fed into my KP value, and that shoots out 54 RPM for my elbow joint motor. So that is going to be fed into the arm system, and based on that, the arm is going to move towards the desired angle. So basically, what happens is, usually the not usually, almost all the time. So this error is the RPM of the arm is always going to decrease with time because the error is reducing, right? Since the proportional part, the error is constantly going to decrease, and it reaches a point where the error is going to become very, very small, say 0.01 degrees. And now because of that, the RPM from the motor is 0.06, which is very, very small. So essentially, this arm just stopped moving. Even though it's almost reached the error, it's never going to actually reach the desired angle. It's never going to reach it exactly. It's going to tend towards it, but it never reaches it. That is one of the shortcomings of this proportional controller. So in order to fix that, we have an integral controller. So what this integral controller does, it has the area of the graph. So what it does is, so with the area of the graph, area of the error time graph, it's gonna multiply its constant or its gain, and then it's gonna add that to the control input. So when we do this, what actually happens is it's gonna reach the input, it's gonna reach the desired input, the desired goal, and it's gonna often overshoot because the area is gonna be very large, right? Even after we reach this area is non-zero, so it overshoots, and then the area becomes negative, and then it reaches its point. So yeah, so we are able to reach our goal, but we're not able to reach our goal. Like, this is not efficient, this is not a good system. So in order to make it better, we have the derivative part. So what this does is, it realizes that the error is getting is it is the derivative of error with time, right? So it realizes the error is rapidly reducing, which becomes negative. So then it adds a negative controlled input to the PID controller, and this helps regulate the system better and prevent the overshoot. Another part where the derivative system comes to use is, often when the system is very sensitive, we get somewhat of an oscillatory motion, like which happens in the inverted pendulum is, it's my pendulum started to oscillate about the desired angles. So the only way to prevent this is to use the derivative part. So I'll explain it to you better once I'm explaining my model. Now I'm going to explain the inverted pendulum, the model of the inverted pendulum on MATLAB. So these are the equations of motions that I've used. So I derived these using the free body diagram shown here. So basically, F is here. I've chosen F to be my controlled input, so I get to push the cart however I want. And then NP are the normal forces, and theta is the vertical angle of the pendulum, and mg is the mass of the pendulum, and I here is the friction is the inertia of the pendulum, and B is the coefficient of friction of the ground. So basically, this the equation I got here is a non-linear equation. So in order to use the PID controller, I need to make this a linear equation. So for that, I've used small angle approximation. So I've taken this sine theta to be 0, and this cos theta to be 1, and this sine theta to be equal to theta, and this cos theta to be equal to 1. So based on that, and replacing f with u, I get these equations. So these are the equations I used to model the system. I'll explain them better when I'm showing you the inverted pendulum's model itself. So now coming to the basic model of the system, so I can show it to you over here as well. So one second, yeah. So here, so I'm opening the MATLAB Simulink model. So this is the model. So I'm gonna put this input here, so it's a little less confusing. So that's the input. So this is my reference signal. This is the angle of the pendulum which I want, which I'm going to keep it to be 0. I want it to be vertically standing, and then based on that, use and I subtract the reference, the state of the system to get my error. That's here. That's measured by the scope, and the error is fed into the PID system. And then we introduce a disturbance. I've introduced the disturbance to be an impulsive force, because when I use an impulsive force, the system becomes stable and becomes solvable. If I use a disturbance which is not an impulsive force, it's almost not possible to stabilize this inverted pendulum system. And then it goes into my system of the inverted pendulum, which I'll be explaining in a bit. And then the cycle continues with the feedback. Okay. So I've used two scopes here. Both of these scopes actually give the same value, since the reference signal is 0. So I actually had to have only one, but I have two here. And I've generated most of the graphs using this code in MATLAB, because I personally like it to get the graph immediately without having to open the scope. It's just a personal preference. So now I'll go back and I'll explain the model. So here, as I mentioned before, the reference angle, this is the controller, the error, the disturbance, the inverted pendulum, the scope, and the feedback loop. Okay. So now I'll explain how the inverted pendulum model is. So I'll just open it on MATLAB to just show you that it's the same. So here's my inverted pendulum. It's the same thing. So I'm going to explain the same thing. I've taken a screenshot and put it into my notes. So you see the bottom block. So this part, this is actually the X double dot part. So basically what happens is, I have my controlled input U that is coming in from here. So what I'm going to do is, I'm going to U, I subtract minus B X dot. So that is this part. So this is giving me minus B X dot. And this part is adding M L theta double dot, from which is coming from here. Okay. So that comes, and then I multiply that into a gain of 1 by m plus small m. So that gives me my X double dot. So that is here, right here, X double dot. Okay. So now I finish this X double dot loop, and on top I calculate my theta loop. So here what happens is, so to calculate theta dot, that's this part. So how do I get it is, so initially I multiply X double dot into a gain of ml. So here I have ml X double dot, and that is being added to mg theta naught. So mg theta, so mg L theta. So that is being added here, and that gets a gain of inertia plus ml square, and that gives me theta double dot. And then I integrate it once, I integrate it twice to get theta, and that theta is fed into, but that theta is being measured. That's the state of my system. Okay. So that is the model of my inverted pendulum that I've used. And now I will show you the graphs that I've got. Okay. So to explain this model, I have actually noted a few values that explain it the best. So first I'll show you when I put all of my values to be 1, kp, kd, and ki to be 1. And I'm running it. So what happens now is I get a very unstable system. Okay, so it's so unstable that I can't actually see it. Okay, so basically this is a very unstable system. So this is not how this works. So with kpk and kd equal to 1, I was getting a very unstable system. So then what I do is I make this value, I increase kp a lot. Okay, so what happens now is when I increase kp a lot, I get an oscillatory graph. So this is, if you remember, I spoke about this before. So this is an oscillatory graph, and this is stabilizing. It is stabilizing, but it's stabilizing very late because my ki and kd values are non-zero, right? It's still one, so that's why it's stabilizing very late. So the way I discussed, the way to fix this was to increase my kd value. So let me try doing that. So I increase my kd value to say 20 times of it. See, so now it's not oscillating; it's just stabilizing pretty fast. Okay. So this is a good thing, and I tried modeling it many times, and I found out that this value is the best. Like, so 120 and I think 30 or 25. You can keep trying to model it. Like you might get a better output eventually. So this is the one that I thought is the best. So the system is stabilizing before 1 second, and the error is like very small. So it has three zeros before I get the error is the theta angle. So this is actually giving me a very good inverted pendulum. And you might be wondering where this inverted pendulum might actually be used. So if you've seen those scooties or those bikes in the mall and all, so you have a bike which has wheels like this, and then it has a handlebar like this, and a person can ride it. So let's say that's my person. He can ride it holding it like that. So these type of bikes are usually more controlled using a PID controller. It has a mass sensor to get the mass of the person, and based on that, it stabilizes this. So this is how the inverted pendulum is. And this MATLAB way to simulate it was actually fun for me, and I think it was really intuitive as you get to see how the graph actually evolves with time. So yeah, that was my presentation for this project, and thank you.